go here.
Turn around.
So good, we're collecting the homework, and a couple of problems on the homework had to do something to do with this interval for a proportion. And I kind of got, I did backwards what planned, so we got a little bit of a head there. And in any case, the new homework will be posted that would do more with the t-distribution and so on. So but today we're going to do the formulas for the confidence interval for proportion. Good opportunity to ask questions. We'll check, writing down some formulas. Everybody can work on some problems. And then we'll do some things with sample size. So we have a formula for the standard error, for the margin of error of a confidence interval. We can do planning. A lot of that's dependent on sample size. So we can pick a sample size for a study to get a certain level of accuracy. Right? So in confidence intervals for proportions, we have some population. And there's some characteristic or some condition that we're interested in. And P is the proportion associated with that in the population. And we're asking the basic question, what is that proportion? So we do something to gather data. And it's really like a binomial experiment. In trials, X equals the number of cases that have that characteristic, the number with the characteristic. And so you can take that number of times out of that and turn it into a sample proportion. P with a little hat on it. The number over n is our sample proportion. And that's our estimate of the population one. But we want to reflect how accurate we think that is. So we want to put a confidence interval about it that reflects the sample size and some other things. So we want to go back up here, and we're going to do a confidence interval for P. We always do confidence intervals for the population proportion, for the population value, because that's what we don't know. We take our sample, and we're going to try to make inference back up to the top. We know a few things from probability when we look at the binomial distribution. We know things about the variance of X, and we can get things about the variance of P hat. The expectation of our sample proportion is P, so P hat is called unbiased, statistically unbiased for the population one. That's good. The variance of P hat is P times 1 minus P over N. This occurred because in the binomial, within trials and a probability of P, that the expected number of successes was within times P, but the variance of the number of successes had this formula of N times P times 1 minus P. And then if you divide by N to get P hat, the N in the denominator gets squared. Right? And so the variance of P hat ends up being that thing. So it's related to the underlying probability distributions where we get this special formula for standard errors. If N is large enough, which NP greater than 5, N times 1 minus P greater than 5, or maybe greater than 10, I guess it's something like that is the usual cutoff. Kind of in degrees, you want the sample size to be larger. If N is large, then P hat is approximately normally distributed, about P with that standard error. We kind of use that basis in probability theory then to make an interval. Right? And so it's the interval that you use for those couple of problems on the homework, the p hat plus or minus the z value times the standard error. And I'll write that on the next page. But the complication here that's a little bit different than the normal one, with the mean, with the mu and a separate sigma, is that p's in there. So it's given the fancy name of the plug-in estimator when you just take p hat and plug it in for p. And so the confidence interval. So confidence interval for p has this form of p hat plus or minus a normal value. P hat 1 minus p hat. It kind of looks like the normal one. If you write it, p hat 1 minus p hat, square root of that. The square root of n is in there just like it was for the normal one. The normal one had s or sigma over the square root of n. This special case, when it's kind of a binomial model, that corresponding thing has that form. Right? In general, it's like the other one, because you have p hat plus or minus your estimate plus a distribution value times standard error. Right? And that's the particular standard error that's up there. Right? And we use normal. Right? So 95% confidence intervals, you're going to use z of 1.96. If you change that, you got to figure out what the other z values are. If it's 99, z is bigger. So that's about the value that's used for that. So that's wider. If it's a smaller confidence interval, you allow it to be narrower. So z 6.05 is the approximate value. Right, that you see as plus or minus that multiplier. So they get wider for more confidence, narrower for less. So let's look at an example. Let's use, so I posted an article. I was looking for an example, kind of a current example, and one place that's kind of interesting to look at is the CDC has this mortality weekly reports. So weekly reports on things that are affecting national health and well-being. There's the one I looked at was this one on MRSA. So penicillin, methicillin-resistant bacteria infections. What are the rates of those? But they had other ones on other staphylococcus aureus infections in veterans hospitals. They had hepatitis B control, foodborne illnesses, and so on. They had another report on how much women are using e-cigarettes and things like that. So any of these have different proportions, different confidence intervals, different significance tests from hypothesis testing. This particular one had an article with some link to some other ones that talk about the rates at which these are happening. And let's see, this is the, I found a different article that I posted on our sites of incidence, prevalence, and management of MRSA bacteria across different populations. So a review. One thing that's in this article are things on the table here, if I can make it show up. This table, right? Maybe it's a little bigger. Not that you have to memorize any of these numbers or have anything here, but it has a bunch of different ways of testing for this disease. Right? And then it reports sensitivity, specificity for these different types of tests. So how should hospitals test if somebody comes in with a serious infection? Is this infection actually resistant? Right? And so a number of studies have done this. It looks like there's culture at 48 hours. That's 2 days to run a culture. Right? There's this chromogenic media at 18 to 24 hours. That saves a day. Or PCR. I don't know how long PCR takes, but they report sensitivity values or specificity values, and then confidence intervals, because it's a rate of testing positive or negative out of a sample size. So it's kind of a binomial experiment to actually estimate what those things are and decide, should you is one of these better than the other? So the example is going to be kind of based on those, if not exactly the same scenario, right? So let's do one example here. So testing for MRSA. And so the 48, so sensitivity was the probability that somebody tests positive, given that it is a true positive. True positive means that it is a methicillin resistant bacteria. It is resistant. And testing positive, the test, the 48-hour culture test, testing positive shows that it is resistant in a particular sample. So imagine you had 50 samples. And the estimate 0.869 is the rate at which, 0.869%. I'm not sure if you can actually get that percent based on this, but we'll go ahead with that, just because I expect that number. So it really would have to be something like 0.58, 0.56 if I only have 50, but let's just kind of ignore that little thing for now. Suppose that's the sample rate. So the sample proportion, positive. Right. That's an estimate of the specificity, right? If we had 50 samples that were really MRSA and we tested them and a certain percentage came up, that would be our estimate of the sensitivity. What's a 95% confidence interval for that rate? Well, 95%, we know in this type of problem we're going to use the normal value. And the formula was p hat plus or minus our z value times standard error, or p hat plus or minus our z value times p hat 1 minus p hat over n. Square root of all that. So 0.869 plus or minus the 1.96. And the square root of the standard error, 0.869. 1 minus that over our 50. And so that 0.869 plus or minus the margin of error there, kind of that half width, 0.0935. And we get an interval 0.775 up to 0.963. The interval in the paper is a little bit different, but it's really done a little bit differently. You can see these different studies that they weighted together, and so there's a little bit more to that calculation, but it kind of, it's not too different from this, not too different, right? So what would that interval mean? How would we, if you needed to summarize something for this mortality, morbidity report and have these data, what would you say? So this, what is this a 95% interval for? What are we trying to determine?
The sensitivity.
Yeah, we're trying to determine the sensitivity for this 48-hour culture test of MRSA. Right? So we're 95% confident that the sensitivity is between 0.775 and 963. Write that, so we're 95% confident that sensitivity of the 24-hour, 48 hours. For MRSA is in that interval. So now you get to do one, and if you have the calculator, you can calculate a lot of it out. Otherwise, you can set it up with the formulas. There were 3 others there: PCR, the 18 to 24 chromogenic. There must be some type of coloring of the bacteria, and then the 48-hour chromogenic. Right. And imagine in each case you have 50. For this one, p hat was 0.925. This one was 783, and this one was 876. So it's a 95% confidence interval in these cases. So maybe these 2 rows could start with this one, and these couple of columns could start with this one, and these couple could start with this one as your, yeah. You can also do the others as well. The next step we're going to do after this is think, well, what happened if we had 200? How would things change? So. Questions? Anybody? Have you come to anything you want to ask? Just Does somebody want to report on one of these? Somebody want to, yeah.
For the first one, the PCR.
Yeah.
I got 0.852 to 0.998.
98, yes, I agree. What would be your calculation?
Wait, for the 200?
Oh, just for the 50.
What do you
What did you get? Well, did you also do the 200?
Yeah.
Okay. What did you get for the 200?
0.889 to 0.962.
A lot closer, right? Yeah. What was the formula you used for the 50? PCR equals.
I had 0.925 plus or minus 1.96 times square root 0.925 times 0.075 over 50.
Yeah, right. Yep. That's what I got. And the 200 one is just a change of 200 there, right? But it becomes a lot more narrow. Right? You have more information, standard error is smaller, it's more precisely estimated. Does anybody want to report on the middle one? Or tell me the values you got. Are there any questions about, or how the first, the third one? 24.8. You want to do the second one?
Yeah, when n equals 50, I got a range from 0.873
0.873 for
the third one.
for the third one. Oh, you
Yep.
did that one. 0.873 is going to be a little bit narrow. But what was the top value you got?
Top value was 0.879.
0.79. So that's going to be a little bit narrow for that. You might want to see. Maybe there's a square root or something. So, what did you get?
I got 0.7846
Okay.
to 0.9674.
So let's look at what went into that formula. What did you write to the formula?
I wrote 0.876 minus 1.96 times the square root of 0.876 times 1 minus 0.876 all over 50.
I think if you don't take the square root, right, because with decimals, the square root makes it bigger, right? So the square root of something like
Yeah, I think I actually just
0.04 becomes 0.2, right? It becomes bigger. Because 0.2 times 0.2, you get 0.04, you get the 2 decimal places. So if you miss that, you know, that it could make it smaller, but I think that's probably right without that, but the square root is that. And then, you know, plus or minus to do the other one. What did you get? Did you do the n equals 200?
Yes.
Okay, how did that?
Got 0.8376 point
Uh-huh.
to 0.9217.
So more narrow. All right. More estimated. And how about the middle one? Yes.
For the 50, it was 0.6693,
6693, okay.
and then 0.8967.
8967. Good. What did you do, 200?
Yeah. And 0.73 and 0.4.
7, 3, and 8, 4, you said?
Yeah.
Yep, I got those numbers. It would be kind of the same process of plugging them in. Right, great. Right. So of these different ones, right? If we looked, this is the table from the article. It's kind of similar to what we got, but of course, they're combining studies and doing things a little more complicated. It's actually called a stratified analysis because they have these different studies, each with their different binomial samples put them together. It's a slightly different formula. It would be probably a formula called like Mantel-Hansel thing for stratified proportions. It'd be kind of at the end of our book. So the actual methods they use for studies like this are not much beyond what we're actually doing. If you had to choose one of these things for diagnosing an infection, which one would you like to use? A little bit. That.
That's already broken, so.
Okay.
But anyway, so among these, right? PCR? Yeah, highest of those, right? Is there anyone that looks conclusively lower in sensitivity than PCR?
Chromogenic for 18 to 24.
Yeah, chromogenic media 18 to 24. Its confidence interval is 71 to 84, where this one's 87 to 90. So this one, the estimated proportion is we're really sure that they're just in different regions. They just don't, the confidence intervals don't overlap. And so really those methods must be really quite a bit different. A number of these others, the other ones kind of overlap some. So we'll get into testing, comparing two proportions, how you would actually kind of synthesize two intervals together to do kind of one interval for a difference. We'll do formulas that will do that. But at this point, the quicker one, the chromogenic media, doesn't seem to have quite the ability to distinguish that. Right? Although chromogenic media did very well for specificity, right? Amazingly well with that one. So, but any questions about the intervals that we've done? Now, I need to backtrack just a little bit because we really do want n large enough, right? Something like n times p times 1 minus p greater than or equal to 10, or n times p, and there's kind of a couple ways that's phrased. We just don't want it too small. So for the PCR one, for sensitivity, p hat was 0.925. And if we really had just 50 based on that, n times p times 1 minus p is a little bit small. We'll put a p hat there. It's a little bit small for the normal approximation to work out so well. So 50 times the 0.925 times 0.075 is about 3.5. So it's a little bit on the low side. Is 3.5. So that's a little low. Right. So that would suggest that intervals that we made for the PCR up here with that kind of normality, something might not be too accurate. Maybe it should be a little wider or narrower, so the coverage is a little bit less precise. There's something wrong with doing that procedure, but it'd be better with 200 to use the normal approximation. Right? Up here, so we probably worry or have a little caveat that the sample size is a little bit small. Take this with a grain of salt. It might not be exactly in these limits for 95%, but still, it would give some indication. Yeah. maybe we should go down to 0.83 instead of down to 0.85. So I think it would be that drastically off from that. Doing these things in R, there's the methods that we have are encoded within R. Right? So we're going to back up to what's up top. There's a command called prop test, proportion test. It could be a test of proportions. And one byproduct of this test of proportions is a confidence interval. Right? So if we do a prop, let's see, 50 times 0.925 is about 46. So if you do prop.test and say we had 46, so x is 46 and we had 50 individuals, it will give us, it's a hypothesis test, is that proportion equal to 0.5? We don't, most of that part in the beginning there is of no use to us right now. Zoom in. Most of this stuff on hypothesis tests is not particularly interesting to us right now. Eventually we will understand everything there and do the hypothesis test. But it also spits out this confidence interval for us there. Right? And so that would be about this. It does something called this continuity correction, right? That the book will talk about. We're not using the continuity correction when we actually calculate our formulas. But it had to deal with the fact that we only have a discrete number of outcomes. We have integers, 50, 49, 48, and so on like this. But the proportions, we're doing something on a continuous scale, or normals a continuous scale. So it either adds 1/2 or subtracts 1/2 the right way to make it a little better fit, a little bit better approximation. Right? But anyway, that's encoded into that. So running that, this would be our confidence interval. You might round it to 0.80 up to 0.97 for a little easier communication. To match our formulas, you can turn off that option. Is this correct? Equal 90 confidence level, default is 95%. You can turn that thing off. That changed the confidence intervals, right? A little bit. It was a little bit wider with that correction, with the small sample size. And that's kind of the difference between the normal being okay versus the normal a little bit off. Right? There is a different procedure. There's a bunch of stuff down there. There's also something called a binomial test for an exact procedure. There's something that doesn't assume normality, and that's described in the book. We're not going to do the hand computations of that, but this one would give a confidence interval without assuming normality, actually looking at the chances of different probabilities under binomial formulas. That works pretty much the same as well. Binomial test, you give it the number of cases, the number of sample size, and it will give you binomial test. So if it was 46 and 50, it will give you a confidence interval. That's a little bit wider than the other ones. But actually 0.8 to 0.98 is pretty close to this one with this correction. So there's not, they're pretty consistent with one another, even though they're slightly different formulas. But they're all doing the same thing. They're trying to tell you where the population proportion is. So that you can make a confidence statement that I'm 95% confident that it's an interval. And these slightly variations of methods use slightly different numbers. But they're really trying to go at the same goal. Any other questions? Now we've done confidence intervals a couple ways, for a couple things. And we can use these formulas to look at sample size. Right? How many cases should you have in your study? So for a proportion, our confidence interval was p hat plus or minus a normal p hat 1 minus p hat over n. Right? So our confidence interval is p plus or minus some m. This m stands for margin of error. P hat plus or minus some amount. If we have our desired accuracy, we want to be plus or minus 3%, plus or minus 2%, plus or minus 10%, right? If we choose this as a goal, the Z is going to come from our confidence level. So for 95% confidence, our Z is going to be 1.96. And if we want a certain margin of error, let's set these things equal. We're going to set M equals Z P hat 1 minus P hat over N. Now Z, if we have some idea of P, maybe from a pilot study or just our general knowledge, and Z is based on our confidence interval, this is something we've chosen, we have an equation here and we can solve for N. Right? So if we square both sides, it'll get rid of that square root. If we multiply both sides by N will show up on one side and cancel on the other. And if we divide by M squared, it will cancel on the first side but show up on the second side. So you can rearrange this thing to say that N is Z squared P times 1 minus P over M squared. You can keep the hat there for now. And so that gives us an equation so that if we use this sample size for a given confidence level and margin of error and value of P, it will give us a sample size we should use for a study. Often in study planning, you don't know what the result's going to be. You won't know what P hat is. So sometimes this is expressed as you should put some value of P in here, or P star, something that's a reasonable guess of P so that you can get going and get a sample size. Yeah?
What does it say under margin of error?
Margin of error, this is where you choose the level of accuracy that you want. So let's do a numerical example. This is the letter M here. So for 95%, we're going to use Z of 1.96. The conservative thing to do is to use P of about 0.5. P of 0.5 has the biggest variability. Yes?
Just to confirm, so if we're going to do this with a normal distribution, are we always going to have the Z and M values be the same?
M could be, M is depending on what you want. Right? So let's say we want to do estimation of the estimate plus or minus 5%. Right? Then M is going to be 0.05. Right? So that would be something you would choose. Right? And so then, if that's enough, then to calculate a sample size. So N would be 1.96 squared. That P star is 0.5. 1 minus 0.5. And then the M squared is 0.05 squared. And this comes out to be about 384 or so. So it suggests to have a confidence interval where the result is going to be P hat plus or minus 5%. At 95% confidence, you should interview or get data from about 384 people. Sometimes polling organizations round this up to 400. Some of them will say, we interviewed 384 people. Right, based on that calculation. If we wanted, say, a margin of error of 3%, so our interval is going to look like P hat plus or minus 0.03. So, P hat minus 0.03, P hat plus 0.03, right? We want that accuracy. What's our sample size then? Same formula, 1.96 squared. We use 0.5. Minus that. The margin of error, if we chosen that we really want to be more accurate, right, then we're going to have 0.03 squared here. And I think I remember it, but let's check. Right? Right, if we calculate that, 1.96 squared times 0.5 times 0.5 divided by 0.03 squared, 1,067. 1067.1. 1067.1. So it would probably be good to round up to 1068 for a sample size. And so sometimes the Gallup poll, when it does its quick national polls, will interview 1,067 people and report estimates based on that. They're aiming at a margin of error plus or minus 3%. What if it's not near 0.5? Well, 0.5 actually produces the biggest sample size. Right? It's the most variability. At 0.5, you're equally likely to go add one or not add one. Anything else is more clumped, up towards 1 or clumped towards 0. So there's less variability. This has the biggest variability in the confidence interval. If instead you thought that was P was something like 0.3, right, then N is going to be 1.96 times 0.3 times 1 minus 0.3 over 0.03 squared. And that comes out to be about 384 again. Right? It's, the reason that's working out is due to these 0.3 over, that's not what it's going to be. That's not what it's going to be. Let's do it a little bit different, right, than that, right? So if we changed it, 1.96 squared times 0.3 times 0.7, which is 1 minus that. If we wanted a 0.03 accuracy, 896, right? 896.4, 897, 896.4, so round up to 897. And so you might be able to get by with a smaller sample size for that same accuracy, as long as the thing you're estimating is about here. It doesn't change too much, right? In the numerator up there, you have 0.5 times 0.5 is 0.25. In this numerator, there's 0.3 times 0.7, which is 0.21. So it doesn't change the sample size all that much within that range. So people often, any large-scale survey, you probably aren't estimating one thing. You're estimating a dozen things, or 2 dozen things. Some of the proportions are near 0.3. Some are near 0.03, and others are near 0.5. So in planning, people often take the conservative approach and take the 0.5. But yeah, so that would be some idea. What I see also happen in surveys is that people anticipate the response rate. Right? So in this involved was a Veterans Administration survey on healthcare enrollees, and in there's 96 markets, different health markets. They've said that they want about 350 people per market. 350 per market means that within each market, everything they estimate, well, it's not going to be quite plus or minus 0.05. Right? So plus or minus 0.05, they need to be 384, but it's not going to be much, plus or minus 0.06 for major things within there. But they think that the response rate is about 30%, or historically has been about 30%. So they're actually going to send out 350 divided by 0.3. So some bigger number of, what is that? Can't do that in my head. They're actually going to send out, so 350 divided by 0.3, about 1167 contacts per market. So 1167 per market. And actually, the response rate, they know the response rate in some areas is worse than others. So they're going to differentially set that. Some places will get 2,000 in hopes of getting 350. And others will get, 900 or something like that, because the response rate in some communities is better. But they use this stuff in planning and accuracy. So they get adequate response to, there's a bias issue of people not responding, but that's different. different thing altogether. But anyway, any questions about? No. Just so that we do one other thing. The other confidence interval that we were doing for a mean, there's a sample size formula that we can use for that one too. And so our intervals at x bar plus or minus the t-value, s over the square root of n, right, is the preferred way to make a confidence interval based for a mean. Prior to that, we did x bar plus or minus a normal value with a sigma over the square root of n. This is the one we really want to do it in practice. This one gets a little bit more used for planning. Right? These both have kind of the idea of x bar plus or minus a margin of error. And so if you set the margin of error equal to the formula, again, we're going to choose the margin of error. We want to be plus or minus $5, plus or minus $10, some quantitative thing like that. And then standard deviation. We'll have some idea of the standard deviation. Pilot study, general knowledge, subject area knowledge, past experience. So if we square both sides again, the square root goes away. We multiply both sides by n. So you get n squared equals z squared sigma squared. We just divide both sides by the margin squared. N is here, z squared sigma squared over m squared. And so, just to get some numbers, there's what I've loaded in here is a data set about people going to the intensive care unit, right? And there's age, race, a bunch of other things, systolic, heart rate. So if we try to make up an example based on estimating age, right? The mean individuals, the mean age of people going to the ICU is about 57. The standard deviation of those is about 20. So let's say we want to estimate the average ICU age within, say, 2 years. How many people do we actually have to talk to? How much data do we have to collect? So the goal is to estimate average ICU age within plus or minus 2 years. So for this quantitative variable of age, it's in years, and our margin of error, is 2 years. We use 95% confidence interval. We're going to use Z 1.96. And based on these data and our guess at sigma, right, maybe these 200 have a pilot study. And we've got data on 200 people. It's about 20. Standard deviation was about 20. So let's use that for planning purposes. How many people do we need to have if we're going to estimate average age plus or minus 2 years? The formula says n is z squared sigma squared over n squared. So 1.96 squared. This is 20 squared. And m was 2 squared. So this one works out nice. That's 100 times that thing squared. That's 384 again. I didn't really mean it to come out of the same number, but it's just right again. So we had 200 in our sample. With this little adjustment, said, well, maybe we should plan for 384 going forward. If you did this study in one area of the country, like in one of these markets, and came up with this and say, maybe you could just use that as planning. Now, if you're going to go out to the other 95 markets, maybe do a little bit more sample size in those to get better accuracy. Right? So these are some of our basic illustrations of confidence intervals. I think you come back on finally started introducing hypotheses. That's another way of saying something about the population. And if you still have the homework paper, be sure to drop it off.
So you're gonna be here for the next like 10 minutes, or should I just wait out in your office?
Or just my office, so it's
Yeah.
259,
Okay,
John Murray 259.
okay, yeah, I'll drop it off.
Okay,
Thank you so much.
yep.
Have a good day.
There you go.
Thank you. Thank you for your time.
Oh, sure.
Thank you, everyone.
So I wanted to talk to you, I'm doing a project for my math seminar. It's like kind of like the final project of like the whole curriculum, the math major.
Yeah.
And a lot of like what I've been, so like right now we're just formulating what we want to study or like what we want to present. It's pretty much just a 30-minute presentation or
Okay.
talk that we're performing in front of the class and stuff like that. And he gave us like a option of picking our topic and stuff like that. So I thought,
Who's running it? This
Professor Simons.
Simons,
So I was thinking of doing like statistical work of some sort. I haven't really decided on what I want to do it on yet. But since that's the field I'm going to be going into, I thought it'd be a good time to start doing some
Yeah,
examples
right.
and stuff. So I was thinking, I mean, if I have any questions or anything, if you're okay with me, just
Oh,
emailing
sure.
you.
Yeah,
Just
email,
talk
or we
about-
can, stop by for half hour.
Yeah,
Thank you.
that would work totally fine. I mean, just in case I run into anything, I need some sort of inspiration of
Yeah.
talking about what.
We could, spending a little bit of time together, going over something.
Yeah.
And then maybe there's a lot of ground we can cover in person.
Absolutely.
Together, and then follow-up emails and stuff.
Exactly, yeah. It's not for quite a long time, actually. I have the outline of the project's just due next Tuesday, so.
Okay.
Up until now, I'll be thinking about things to do and what I
Yeah,
want to
yeah.
work on, and things like that. But once I get the ball rolling, if I could come in and talk to you
Sure.
once a week, or maybe even once every 2 weeks, or anything like that,
Yeah.
just to get the ball rolling.
Right there's about halfway through the semester. So
Exactly.
There's only a couple months.
It won't be quite as large as the one that we did in Math
Yeah.
490.
Right.
I'd probably do more of like a simplified version, I guess, because I don't remember how long the presentation was in Math 490. I think it might have been like 15 minutes.
15 minutes, yeah.
So-
We did less.
Exactly.
It was more the experience of going over things
Yeah, it was
together.
good
and
to
then-
get into that type of
And it was writing up a summary.
report and everything,
report.
which we will have to do. But so the presentation is basically, I think he said at max a 30-minute, and it's more of like a discussion too. Like
Yeah.
so, I guess a lot of what I've been thinking about is I want to kind of do it like. I want to do my presentation kind of like how Desjardins did his, because like
Uh-huh.
he presented a model, and
Yeah.
I don't know if I'm going to do something like that yet. I haven't really thought about a topic and how I'm gonna kind of explain my hypothesis or whatever, and
You doing something in
statistical
sports
format.
or?
I honestly, I've been thinking about it. I've gotten to a lot of like just like walls of where I want to, like my area of interest at this point. It's not that I don't want to do something in sports, but I definitely want to do something like in a more broader range. So if it had to do with sports, maybe with some concentrations of like finance. So I've
Yeah.
also been thinking of like how viewership in baseball has gone down over the years, just
Uh-huh.
because of like the speed of the game and different things like that. So I was thinking that might be interesting, but it's also like I don't know how to draw in all of the things I want to do. I don't want to bite off more than I can chew. But I don't know. I'm gonna think about it for a while, maybe over the weekend and stuff. And if I just wanted to know if I had any ideas or if I wanted to come in.
Well, you know, one possibility would be investigating, you know, getting players' data, and then maybe pulling in, linking in some data sources and kind of getting a nice data set without having to kind of hand enter a lot of stuff. You know, maybe it's, you gotta do a little processing of stuff off the web or something.
Yeah.
But techniques like classification or clustering,
Yeah.
so if you applied that, some things, you know, there's a technique called k-means clustering, where you have a bunch of variables, and you are essentially looking at Euclidean distance between the centers of clusters and all those points.
Yeah.
So it's just the sum of squared distances in this cluster, and you postulate that there's a number of underlying groups
Yeah.
or types.
And that they're associated some. in some
And then they
way.
get kind of clustered around their averages, like you have the high hitters and the low hitters and the
Yeah.
ones that are getting, you know, stolen bases and the one, you know, but you don't preset them.
Yeah.
You just let it
Let it happen.
be discovered.
Exactly.
And you can put in as many variables as you want and see what it comes out, and then describe
Kind of what's going
what's
on.
going on. There's a k-means, kind of the goodness of fit statistic. As you add more clusters, it keeps going down, but it's something they call a scree plot. And it's just, you know, as you add more and more clusters, this goodness of fit thing goes down and it goes down, but then eventually it settles out.
Yeah.
And so that's one tech. There's a kind of a computational issue of how do you do that efficiently? How do you find the best positions those? And there's something with like trading off. It's kind of a combinatorial thing behind it, but it's kind of an entry level of clustering
Yeah.
things that could be used. There's a k-means in R, I'm sure. I'm going to shut R, but so there's some algorithms in R, which
Yeah.
get the data in there to do it. So I'm sure there's a help of k-means. Yeah, there's a k. Okay. Yeah, see, there's a k-means clustering algorithm that comes with the default. You put in all your data X, a big numerical.
Big data set of
Yeah,
whatever.
yeah, and then you do the centers.
Yeah.
How many centers you want. There's different algorithms for finding this, the solution, and then you can show the different objects. And there's a few algorithms. John Hartigan was at Yale for a long time and wrote these algorithms, like in applied statistics. But anyway, and then there's some examples you could play with. Kind of like an analysis of variance. There's a between group sum of squares,
Yeah.
or within group sum of squares, and
Okay.
some testing. So that would be one way to explore a clustering algorithm.
Yeah.
Things. The data set that, like Major League Baseball,
MLB, yeah, MLB.com has a lot of good data.
like on like player statistics. One of these things has, you know, like these things. I'm not sure exactly how, but you can just kind of highlight all of this and drop it into an Excel file.
Yeah.
Right, and then you get all those players in there, and then you get
Put that into R.
get that into R.
Yeah, I know how to.
Cluster by, you know, cluster all these variables to see if any patterns come out.
Mhm.
you know.
So this is kind of like almost like doing a project, but starting off not knowing what your hypothesis is, and then kind of developing it after you read the data.
Yeah, so it's kind of, it's applied statistics.
Yeah.
Rather than the mathematics of it.
Yeah.
I mean, if you want to do something computational within mathematics, you would be looking at one of those articles on the algorithm. How do they actually do this?
Mhm.
And minimize this criterion. It's minimizing sum of squared error function.
Oh wow.
And there's a numerical way that they do it. So there's a numerical computational issue behind it. but then it can be applied to things like that. So
Okay.
it's, you you might try to find, I have books on clustering, so maybe I could lend you a book that deals things like this. But this algorithm, it looks like there's a link to it. So JSTOR is just free.
Yeah.
And so the applied statistics k-means algorithms. Let's see, he has a book, Hard Again, and then I think this is going to be code. So it kind of describes this.
Describes the algorithm.
Yeah, it's a Fortran subroutine. It's a public, what we published. Time and accuracy. So anyway, it's so here's this Fortran subroutine for you. for doing.
Fortran, oh my gosh. Isn't that like the earliest, that's like one of the earliest.
It's
days
early.
of
I mean,
computer
Fortran,
languages.
in high school, I had a book called Fortran 77.
Uh-huh.
And,
I mean, when I took my programming languages course, this was the first one we learned about because it was just like the basic one. But it was one that was so, I don't know if it can be called outdated, but it was just from.
So there's a
Yeah.
Fortran 90, so there's some updates to it. I mean, one thing about this is it uses fixed vector and matrix sizes, array sizes.
Yeah.
So you kind of specify everything up front.
Yeah.
And it's not kind of like flexible on the go. There's ways to do it, like you have a source file where you're reading parameters, and then that adjusts the matrices and all that stuff. But it's not as object oriented as
Yeah.
as
Java.
yeah, and it's kind of C supplanted some of the things with it. So, but anyway.
All right, but so wait, this was good. I mean, I'm already getting my thoughts flowing on what I want to do and kind of what it would take to give it. Because the 30 minutes isn't what scares me. I think I could, even if it was just creating a model, which again I don't know if I'm going to do that, but
Yeah.
it would be like from the presentation we had last time. I probably could have stood up there and talked for 30 minutes. It wouldn't have been as interesting, obviously, but.
Yeah, you can go through more detail.
Exactly,
Sure.
yeah.
So
And
do you want to give a moment to come to my room?
I actually have to run to
You
a
run to the class.
right now. Yeah, I have
but,
like 5 minutes.
but connect with me at some point, because I do have books on clustering that will
Mhm.
describe some of these algorithms.
Yeah.
And that could be kind of a reference to look
Yeah,
at.
that'd be great,
So-
yeah. Maybe, I think I might be around tomorrow to come. I'll just shoot you an email
Okay.
tonight and let you know if I'm gonna be on campus, and I'll come to your office or
Okay.
anything, but.
Sure.
Other than that, this was great, and if I could keep talking to you throughout the rest of the semester, just basically.
And the firms that do data science,